Hey everyone, welcome back. Ready to dive into some graph theory?
Always up for a good graph theory puzzle.
Well, we've got a real treat today. Remember that tree packing conjecture, the one that's been hanging around unsolved since '76?
Yeah, kind of a big deal, right? Mathematicians have been scratching their heads over that one for decades.
This paper claims they've finally cracked it. And, reading through it, their approach is really fascinating.
It's elegant, actually, to think they managed to take this problem that's so visual, literally about fitting trees together.
And turned it into an algebra problem.
Yeah, polynomials of all things.
Okay, so first, can we just back up a bit? For our listeners who might not be as familiar with this conjecture, what's the gist?
So in essence, it says that you can always pack a bunch of trees, those connected graphs with no cycles, into a complete graph.
Complete graph being?
Right. A graph where every pair of vertices is connected by an edge. So the conjecture says you can always fit these trees into this complete graph without any overlaps, as long as the number of vertices in each tree adds up to the number of vertices in that complete graph.
Okay, so it sounds, I don't know, kind of obvious when you put it that way. Like, yeah, of course you can. If they fit, they fit.
Well, proving that rigorously, mathematically, that's a whole other story. And that's what's been so tricky about this conjecture for so long.
So how did this paper finally crack the code? What's their secret sauce?
Well, they started by transforming the whole problem, representing trees in a really clever way as functions.
Wait, functions. I'll admit, when I first read that, I was a little lost. Trees are these visual things, branches, nodes.
Yeah.
How do you even start turning that into an equation?
It's all about representing the tree's structure in a new language. So in section 1, they define a functional tree. They start by labeling each vertex of the tree, right? Giving it a unique number from 0 to n1, where n is the total number of vertices in the tree.
Okay, so each little point on our tree gets a number tag.
Exactly. Then they pick one special vertex and call it the root. Think of it like the base of your tree.
Got it.
Now, here's the key. Every other vertex in the tree has a unique path that leads back to that root. Their trick is to define a function, they call it g, that takes a vertex as input and spits out the next vertex on its path to the root.
So it's like directions. If I'm at vertex 5, this function g tells me which vertex to go to next to get closer to the root.
Precisely. Look at figure 1.1 in the paper, for example. They've got this simple 4-vertex tree. They've labeled the vertices, chosen their root, and then defined g so that, let's see, g3 equals 1, meaning if you're at vertex 3, the function tells you to go through vertex 1 to get to the root, which is vertex 0.
It's like they've turned the tree into a roadmap. But how does this help them actually pack these functional trees together?
That, my friend, brings us to the concept of complete labeling, and this is where it starts getting really interesting.
Okay, so complete labeling. Definition 1.6. Let me see if I can summarize this. It seems like it's about assigning labels to the vertices of our complete graph in such a way that, well, it ensures that when you try to pack the trees in, their edges don't end up overlapping, conflicting with each other.
You got it. It's all about making sure each edge has a clear direction dictated by the labeling so that when you overlay these trees onto the complete graph, everything slots into place perfectly. No collisions.
And they represent this direction using permutations, right?
Yeah.
It's like finding the right order to lay things down so they fit perfectly within the boundaries.
Exactly. Finding the right permutation for each tree is equivalent to finding a successful way to pack it without conflict.
And to illustrate this whole idea, they introduce this example with functional stars, example 1.8.
A simpler case, but it really drives home how this labeling strategy works in practice. And you can see how this approach, using functions and permutations, starts to bridge the gap between the visual problem of tree packing and the algebraic tools they'll use later.
It's really clever. Okay, so we've got our trees, we've turned them into functions, figured out a way to represent how they should fit together. What's the next step in their strategy?
Well, this is where things take a decidedly algebraic turn. They introduce what they call the Tree Packing Polynomial Certificate.
Ooh, sounds intimidating.
Don't worry, it's not as scary as it sounds. Well, the definition itself, definition 2.1, might look a bit intimidating. Lots of symbols and summations.
Those modulo operations always throw me off a bit.
Right, but the core idea behind this polynomial is actually quite intuitive. Think of it like a truth detector for tree packing.
It's a truth detector. Okay, I'm intrigued. How does that work?
So they've constructed this polynomial in a very specific way, taking into account those vertex labels, the g function that defines your tree, and a few other parameters. And the key is, if you plug in all these values for a specific way of packing those trees, a specific labeling, and the polynomial spits out 0 as the answer.
It's a lie. the packing doesn't work.
Exactly. Zero means that labeling, that particular way of arranging your trees, is not going to lead to a successful packing. But if you get any other value, any non-zero result,
Then you're in the clear. You've found a packing that works.
exactly. They've essentially transformed this complex geometric problem. Do these trees fit together into a simple yes or no question about their polynomial? Does it vanish, become zero, or not?
That is incredibly clever. Instead of wrestling with visualizing these trees in all the ways they could fit, they've turned it into an algebra problem.
And that's where the real power of this approach shines through. They can now use the tools of abstract algebra to analyze this polynomial to prove things about its behavior, which is exactly what they do next. So they've got this polynomial, this truth detector, but now they need to show that it actually works, right? That it can really distinguish between good and bad tree packings.
And that's where proposition 3.3 comes in.
Exactly. This proposition sets the stage. They prove that if they can show their polynomial never vanishes, never equals zero, for a specific way of representing these trees, they call it the canonical representative, then they've essentially proven the tree packing conjecture for all representations.
Okay, so they've narrowed down their target. Instead of having to deal with every possible way to represent these trees, they just need to focus on this one, this canonical representative. But why is that even allowed? How can they be sure they're not missing something by making this simplification?
Because they've proven that focusing on this canonical form is enough. They delve into the nitty-gritty details of how they construct this canonical representative. It's definition 3.4 if you want to take a look. But the key takeaway is it captures all the essential information needed to analyze whether or not a particular arrangement of trees, a labeling, will lead to a successful packing.
So it's like they've distilled the problem down to its purest form.
Exactly. And to get there, they use some heavy-duty mathematical machinery. They bring in this thing called the multivariate quotient remainder theorem, which sounds scarier than it is.
Yeah, I'm sensing a theme here.
But basically, this theorem just gives them a way to systematically simplify polynomials, kind of like finding the most elegant way to write an equation.
Got it. So they're simplifying things, but in a controlled way, making sure they don't lose any important information along the way.
Exactly. And to do that, they also lean on this concept of Lagrange interpolation. Ever come across those?
Vaguely, from way back in my math classes, they have something to do with building polynomials, right?
Right. Think of Lagrange polynomials as building blocks. You can combine them in different ways to create all sorts of more complex polynomials.
Okay. And how did that help with the whole tree packing thing?
Well, by using these Lagrange polynomials, they can express their tree packing polynomial in a way that makes its properties, especially this whole business of whether it vanishes or not, much easier to analyze.
It's like they're choosing the right tools for the job. Lagrange interpolation helps them get their polynomial into a form where they can really start digging into its properties.
Precisely. They lay out all of this, the justification for using this canonical representative, in the lead up to the really meaty part of their argument, the composition lemma. But before we get there, they have a few more stepping stones to put in place.
Okay, more setup, more groundwork. I'm starting to see how meticulous they're being with their logic, building this airtight argument step by step.
Exactly. And that's what makes this paper so compelling. It's not just about the result, but the journey they take to get there. So with that in mind, let's turn to the next piece of the puzzle, this variable dependency fact that they present in Proposition 3.5.
Okay, Proposition 3.5, let's see. They start by talking about a polynomial where every term, when you expand it all out, is a multiple of certain specific variables.
Right, so certain variables are like the common factors in each part of the polynomial.
And then they raise this polynomial to some power, and oh, there are those modulo operations again.
Right, they simplify it, focusing on the remainders after division. And what they manage to prove is that even after all that manipulation raising to a power, simplifying with modulo, the end result still only depends on those same initial variables.
So it's like those initial variables are the key, the fundamental building blocks that determine the entire structure of the polynomial, no matter how much you twist and turn it.
Exactly. It's a subtle but crucial point. And while it might seem intuitively obvious, rigorously proving this property is essential for their later arguments, especially when they delve into the composition lemma. And speaking of crucial, let's move on to lemma 3.6, which they've dubbed the monomial support lemma. This one dives into the specifics of those Lagrange basis polynomials we were talking about earlier. Remember how we were picturing them as building blocks?
Yeah, those Lego bricks that light up for specific inputs.
Precisely. Well, this lemma is all about understanding those building blocks in even more detail. They prove a very specific property. Every term in those Lagrange basis polynomials, when you expand them out fully, is a multiple of almost all the variables involved.
Almost all? What does that mean?
It means there might be a few very specific exceptions, but for the most part, every single term in these Lagrange polynomials has this nice property of being divisible by most of the variables.
I'm trying to picture how that fits into the bigger picture. It feels like they're establishing a set of constraints, a sort of mathematical grammar for how these polynomials can be built and manipulated.
Exactly. Remember, they are constructing a very specific polynomial, this truth detector, and they need to ensure that every component, every building block, adheres to certain rules to guarantee that the whole thing works as intended.
Okay, I'm with you. So they've got their variable dependency fact, their monomial support lemma. What's next?
Well, they introduce another key idea, the automorphism invariance lemma. This is lemma 3.9, and it's where things get really elegant.
Elegant, huh? I'm always up for some mathematical elegance.
This lemma is all about symmetry, a concept that pops up everywhere in mathematics and especially in graph theory.
Symmetry, like in those perfectly symmetrical snowflakes.
Exactly. With trees, you can often swap certain branches or vertices without actually changing the underlying structure of the tree. It's like rotating or reflecting that snowflake. It's still the same snowflake.
So you're saying trees can have this kind of inherent symmetry?
Yes. And this lemma essentially states that if you have that kind of symmetry in your functional tree, you can reflect that symmetry in your polynomial as well. You can swap certain variables around, and the value of the polynomial won't change.
So the polynomial doesn't care if you make these symmetrical swaps.
Exactly. It's invariant under those transformations. They've found a way to reflect the tree's symmetry within their polynomial.
That's pretty neat. But why is this invariance so important?
Because it dramatically simplifies their task. They don't have to check every single possible labeling, every possible arrangement of the trees. They can exploit these symmetries, knowing that if it works for one arrangement, it'll work for any symmetrically equivalent arrangement as well. It's like cutting their work down exponentially.
Ah, I see. Symmetry to the rescue.
Thank you.
Okay, we're getting closer. They've laid the groundwork, created this incredible toolkit of lemmas and propositions.
And now, with all the pieces in place, they're finally ready to unveil their masterpiece, the composition lemma.
All right, time to face the music. The composition lemma, it's been looming over this whole discussion, this whole proof. Feels like the grand finale.
It is really the culmination of all their clever tricks and strategic maneuvers, and lemma 3.7, this composition lemma, it's where it all comes together.
So last time we left off with all these lemmas, these building blocks. But how do they actually use this composition lemma to prove the conjecture? How does it help them go from those simplified examples to any set of trees?
Well, the key here is that they don't try to prove it for any set of trees all at once. Instead, they use this really clever iterative process.
Okay, I'm all ears. Iterative meaning.
They start by looking at the largest tree in the set, and they apply a transformation, a specific modification to its structure that essentially collapses a portion of its branches towards the root.
Collapses meaning like they chop off parts of the tree.
Not exactly chop off, but more like strategically pruning it. They bring some of those outer branches closer to the center, modifying the tree's structure, but in a very controlled way. And the composition lemma comes in to tell us that if their polynomial, that truth detector, works for this slightly modified set of trees.
Meaning it doesn't equal zero, right?
Right. If it doesn't equal zero for this pruned version, then it must also work for the original set of trees, the unpruned version.
Hold on. That seems as a leap. Just because they can make it work for this simplified, pruned version, how can they be sure it holds true for any set of trees, no matter how complex?
It's all about the logic, the way they connect the pieces. They painstakingly demonstrate that this pruning operation, while it might introduce new terms to the polynomial, doesn't actually change its fundamental structure, its essence. So if the polynomial didn't vanish before, these new terms can't magically make it vanish now.
Okay, so they prune the largest tree, check the polynomial, and then just keep pruning.
Exactly. They repeat the process. They look at their new set of trees, now with one slightly smaller tree, find the largest one again, and apply the same collapse and proof strategy. And every step of the way, this composition lemma acts as their safety net, ensuring that they're not changing the underlying truth of the matter. If the polynomial worked before, it must work after this pruning.
It's like they're carefully taking apart a complex machine, piece by piece, making sure that with each removal, the machine still functions as intended.
Yes. And here's the beauty. Eventually, after enough of these pruning steps, they end up with a set of trees that are all stars. Remember those?
The functional stars from that early example, 1.8, they're coming back.
Exactly. And remember how straightforward it was to pack those stars together. We even have visual confirmation that the conjecture holds true for sets of star trees. They're almost trivial.
So they've created this chain of logic, this bridge, from this daunting task of packing any set of trees to the almost effortless problem of packing these simple star-shaped trees. And because they can prove it for the stars, and they've shown that each pruning step maintains the integrity of their solution, they've essentially proven the conjecture for any set of trees.
It's a beautiful example of mathematical induction in action. They've shown that if it works for a simple base case, the stars, and it continues to hold true as you gradually increase the complexity, then it must hold true for every possible case.
This is incredible. They've taken a problem that's been a thorn in the side of mathematicians for almost 50 years, and they cracked it wide open.
And they did it by approaching it from a whole new angle. Instead of trying to brute force the problem using the same combinatorial tools that have been used for decades, they found this elegant connection to abstract algebra, transforming the question into something solvable with a completely different set of tools.
It really highlights the interconnectedness of mathematics, how seemingly disparate fields can offer these surprising solutions.
Absolutely. And it reminds us that the most challenging problems often require a fresh perspective, a willingness to think outside the traditional boundaries.
This deep dive has been an incredible journey. It's not just about solving a single problem. It's about the power of ingenuity, the beauty of mathematical reasoning, and the endless possibilities that emerge when we dare to ask hard questions and seek unexpected connections. Thanks for joining us, and as always, stay curious. All right, so get this. We're diving deep into the world of graph theory today. But it's not just any old graph theory. We're talking about trees.
Ah, yes, trees, those beautiful branching structures. Always a favorite topic of mine.
Well, get this, because this is where it gets really interesting. For almost 50 years, there's been this conjecture, right? This mathematical head-scratcher that's been bugging mathematicians. It's called the Tree Packing Conjecture.
A classic problem. Elegant in its simplicity, yet deceptively challenging to prove.
Exactly. And the wildest part is it's finally been solved. We're talking about a brand new proof that's turning heads in the math world.
And it's not just the solution itself that's causing a stir. It's the method they used, a completely new way of looking at trees using, wait for it, functions.
Functions. Okay, now you're speaking my language. But let's back up for a second for those who might not have encountered this tree packing puzzle before. We're talking about taking a collection of trees, each with a different structure. Maybe one's long and spindly, another's short and bushy.
And each of these trees has a certain number of vertices, those points where the branches connect.
Right, the nodes. And the conjecture asks, can we always fit these trees neatly into a complete graph with the same number of vertices?
And by fit, we mean that the edges of the trees, those lines connecting the vertices, perfectly divide up the edges of the complete graph. No overlaps, no leftovers, just a perfect tiling of tree branches.
Like a jigsaw puzzle, but with trees.
Precisely. Now imagine trying to do this for any possible combination of trees you can dream up. That's the challenge that stumped mathematicians for decades.
It sounds deceptively simple when you put it like that, but clearly it's anything but.
It's a testament to the power of combinatorics. The sheer number of possibilities explodes as you increase the number of vertices and the complexity of the trees.
So how did they finally crack it? You mentioned functions. I'm dying to know how functions play into all of this.
Well, it all starts with a brilliant insight. Every tree has a root.
Right, like a family tree.
Exactly. And we can use this root to define a function that maps each vertex in the tree to its parent vertex. It's like assigning each person their ancestor, with the root being the ultimate ancestor for everyone.
So we're essentially encoding the structure of the tree into a function.
Precisely. And this function has a special property. The root maps to itself. It's a fixed point. And it's this fixed point property that allows us to bring in the big guns of algebra to solve this problem.
Okay, now we're talking algebra. I'm intrigued. How do we jump from trees and functions to equations and symbols?
Well, the key lies in constructing a very special polynomial, what they call the tree packing polynomial certificate.
A polynomial. So we're talking about something like x squared plus 2x minus 1, but probably way more complicated.
Oh, definitely more complicated. But the basic idea is the same. This polynomial acts like a truth teller for our tree packing problem. We plug in information about our trees and the way they're arranged, and the polynomial spits out an answer 0 or non-zero. 0 means, nope, this arrangement doesn't work, and a non-zero value means bingo. We found a way to pack these trees.
That's so cool. So it's like a mathematical litmus test for tree packing.
Exactly. But there's a catch. To use this polynomial, we need to consider every possible way to arrange or label the vertices of our trees. We're talking about a combinatorial explosion of possibilities.
Okay, I'm starting to see how this problem got so tricky. Testing every single arrangement would take forever.
Exactly. And that's where the true brilliance of this proof shines through. Instead of brute forcing their way through every possibility, the mathematicians devised a clever strategy using something called the composition lemma.
All right, you've got my attention. What is this composition lemma?
Yeah.
And how does it help us avoid drowning in a sea of possibilities?
Imagine taking a really complex tree and carefully dismantling it into smaller, simpler trees. The Lego bricks, in our case, are star-shaped trees, the simplest kind, with one central vertex and all other vertices directly connected to it.
So we're breaking down a complex problem into more manageable pieces. Classic problem-solving strategy.
Exactly. The composition lemma essentially proves that if we can find a way to pack these simpler star trees into our complete graph, then through a series of strategic compositions, we can ultimately pack the original, more complex tree as well.
So we're working backward, starting with the solution for the easy case and using it to build up a solution for the hard case.
You got it. It's like a chain reaction of mathematical logic.
I love it. But how do we know that breaking down and then rebuilding our trees in this way doesn't mess everything up? How do we guarantee that the labeling, the arrangement of those vertices, still works perfectly throughout the process?
That's where another crucial piece of the puzzle comes in, the automorphism invariance lemma. This lemma acts like a safeguard, ensuring that the transformations we make to the trees during the composition process don't disrupt the fundamental properties we care about, especially the existence of that perfect, complete labeling.
It's like having a mathematical guarantee that our solution will stay intact even as we rearrange the pieces. That's pretty elegant.
Elegance is an understatement. This proof is a symphony of mathematical concepts, each playing a crucial role in creating a truly airtight argument.
All right, you've definitely piqued my curiosity. We've got our polynomial truth teller, our composition strategy, and our invariance guarantee. I'm ready to dive into the nitty-gritty details of this proof and see how it all comes together.
Then let's roll up our sleeves and get into it.
I'm all for it. But first, a quick message from our sponsors. Stay tuned because we're about to unpack the heart of this groundbreaking proof.
So we're picking up right where we left off, diving into the heart of this incredible proof. We've got our composition lemma, right? This idea that we can break down complex trees into these simpler star formations. But there's this nagging question. How do we know that as we're shuffling these pieces around, the labeling, the way those vertices are arranged, still holds up?
Yeah, it feels like we need some kind of mathematical insurance policy to make sure our solution doesn't fall apart as we're rearranging the furniture, so to speak.
Precisely, and that's exactly where the automorphism invariance lemma comes in. Picture this. You've got your tree, right? But imagine you could pick it up, rearrange the vertices, shuffle them around like a deck of cards.
Okay, I'm visualizing it. So we're changing the order of the vertices, but the connections between them stay the same. We're not breaking any branches or anything.
Exactly. The underlying structure of the tree remains intact. Now, the automorphism invariance lemma essentially guarantees that no matter how we apply these shuffles or automorphisms to our tree, if we start with a valid complete labeling, we'll end up with a valid complete labeling. The labeling might look different, but it will still satisfy all the rules, all the connections required for a perfect packing.
So it's like this lemma is saying, go ahead, rearrange those vertices to your heart's content. As long as you're not changing the connections, your labeling is still good to go.
You've got it. It's this incredible invariance property that forms the bedrock of the proof. It allows us to move seamlessly between those simpler star formations and the more complex trees we're trying to pack, knowing that our labeling will hold up every step of the way.
Okay, that makes sense. We can break down our complex trees into stars, solve for those, and then, thanks to this automorphism invariance, we can piece everything back together, knowing that our labeling is still solid.
Exactly. It's like having a mathematical safety net. Now, to truly appreciate the magic of this proof, we need to dig a bit deeper into the composition lemma itself. Because it's not just about breaking down a tree into any old smaller trees, it's about doing it strategically in a way that maintains this crucial property of complete labeling.
All right, I'm ready to get into the weeds. What's so special about this strategic breakdown?
It all boils down to how we define composition in the context of this proof. We're not just snapping branches off haphazardly. Imagine this. You've got two trees, T1 and T2. We pick a leaf node from T1, which is just a vertex at the very end of a branch, and we identify the root of T2.
Okay, so we've got one tree with a dangling leaf and another ready to receive it. I'm picturing it. What happens next?
We merge them. We take that dangling leaf node from T1 and essentially glue it to the root node of T2, creating a single, larger tree. This new tree, which we can call T, is the composition of T1 and T2.
So it's like we're grafting one tree onto the other, using that leaf node as a connection point. And by repeating this process, we can build more and more complex trees from simpler ones.
Exactly. It's like a botanical Lego set. But here's where the composition lemma really shines. It doesn't just tell us that if we can find complete labelings for T1 and T2 independently, then a complete labeling exists for their composition T. It actually gives us a recipe, a way to construct this new labeling based on the labelings we already have.
So it's like we're not just combining trees, we're combining their instruction manuals as well, showing us how to take the labelings from the smaller trees and create a valid labeling for the larger combined tree.
You've got it. It's incredibly elegant. And this is where our trusty tree packing polynomial certificate comes back into play. Remember, it's not just one polynomial, but a whole family of them, one for every possible tree structure.
Okay, so each tree gets its own personalized polynomial, like a mathematical fingerprint.
Love the analogy. And these polynomials are designed in a way that directly reflects the concept of complete labelings. The variables in the polynomial represent the edges of our complete graph, and the coefficients, the numbers in front of those variables, are determined by the structure of the tree and the specific labeling we assign to its vertices.
So the polynomial encodes all the essential information about our tree and how it's arranged.
Precisely. Now, when we compose two trees, T1 and T2, to get our new tree, T, the composition lemma doesn't just magically give us a complete labeling for T. It provides a way to express the tree packing polynomial for T in terms of the polynomials for T1 and T2.
So we're not just composing trees, we're composing polynomials as well, mirroring the underlying structure of our problem at every step.
You're seeing the bigger picture. And this connection is what makes the proof so powerful. Remember how our polynomial acts as a truth teller with a non-zero value indicating a complete labeling? Well, the composition lemma, coupled with this polynomial relationship, essentially allows us to determine the truth for our combined tree, T, by looking at the truth of its smaller components, T1 and T2.
So if the polynomials for the smaller trees tell us we have complete labelings, then the polynomial for the combined tree must also give us the green light, guaranteeing a complete labeling for the larger structure.
You got it. It's like a chain reaction of truth, all thanks to this clever composition process and the way these polynomials interact. And because we know we can always find complete labelings for those initial simple star trees, which form our base case.
We can confidently build up from there, step by step, knowing that our composition process and our trusty polynomials have our backs every step of the way. This is an amazing strategy.
It's a testament to the power of mathematical induction. We prove it for a base case, and then we show that if it's true for a tree of a certain size, it must also be true for a slightly larger tree. And we can repeat this process ad infinitum, climbing the ladder of complexity with confidence.
And this, ladies and gentlemen, is how you conquer a conjecture that's puzzled mathematicians for half a century. It's not brute force, it's not luck. It's about finding those elegant connections, those underlying patterns, and wielding them with precision. I'm absolutely floored by the ingenuity of this proof.
As you should be. But we're not done yet. We've still got to unpack how this proof goes beyond just trees and complete graphs, because believe it or not, this is just the tip of the mathematical iceberg.
Okay, now you're really teasing. I'm all ears. What other mathematical mysteries are hiding beneath the surface?
Well, to understand the true scope of this breakthrough, we need to shift our focus from trees to a much broader class of mathematical objects. Well, to understand the true scope of this breakthrough, we need to shift our focus from trees to a much broader class of mathematical objects, graphs in general.
Okay, so we're zooming out to the bigger picture now. Trees are just one type of graph, but there's a whole universe of graphs out there. with different structures and properties.
Exactly. We're talking about networks of all shapes and sizes, from the intricate web of connections in our brains to the vast network of roads and highways that crisscross the globe.
And each of these networks can be represented mathematically as a graph, with those nodes and edges capturing the essential relationships between the different parts.
Precisely. And many of the biggest challenges in fields like computer science, biology, and social science boil down to understanding these complex networks. How does information flow through a social network? How do diseases spread through a population? How can we design more efficient transportation systems? These are all questions that can be tackled using graph theory.
And I bet this new functional approach to graph theory could provide some powerful new tools for tackling these real-world problems.
You're hitting the nail on the head. By representing graphs as functions, we open up a whole new world of mathematical techniques that we can leverage to analyze and manipulate these structures.
So instead of just looking at graphs visually, as these kind of static diagrams, we could start to think about them dynamically, using equations and algorithms to study their behavior and uncover hidden patterns.
Exactly. Imagine being able to calculate the flow of traffic through a city using calculus or predict the spread of a virus using algebraic geometry. This functional approach could revolutionize the way we model and analyze complex systems.
That's incredible. It sounds like this seemingly abstract mathematical proof about packing trees could end up having very real-world implications.
It's a perfect example of how pure mathematics, driven by curiosity and a quest for elegance, can often lead to unexpected breakthroughs in our understanding of the world around us.
This entire deep dive has been an amazing journey. We started with a puzzle about packing trees and ended up uncovering a whole new way of looking at graphs and their applications in the real world.
And we've only just scratched the surface. The beauty of mathematics is that every answer often leads to even more intriguing questions. The tree packing conjecture might be settled, but the journey through the world of graphs, functions, and their countless applications is far from over.
Well said. This deep dive has been a testament to the power of human ingenuity, abstract thinking, and the sheer elegance of mathematics. And for anyone listening who's feeling inspired to explore further, well, you're in luck.
We've got a treasure trove of resources and links in the show notes for those who want to dive deeper into the world of graph theory, the tree packing conjecture, and the amazing mathematicians who made this breakthrough possible.
And remember, whether you're a seasoned mathematician or just starting to appreciate the beauty of numbers and patterns, there's always something new to discover in the vast and ever-expanding universe of mathematics.
So stay curious, keep exploring, and who knows what mind-blowing discoveries await you just around the corner.
Until next time, happy exploring. You know, sometimes in math, you find a problem and it seems so simple, but then you dig deeper and it just explodes with this like crazy depth, and it can end up stumping mathematicians for like forever.
Yeah.
And today, we're tackling one of those problems, a real head scratcher that's been around for almost 50 years. The tree packing conjecture.
The tree packing conjecture, a classic. It seems almost obvious at first glance,
Right.
but the more you look at it, the more you realize just how complex it actually is.
It's a perfect example of something that sounds easy until you try to, actually prove it mathematically.
Absolutely.
And the really cool thing is, it's been proven recently. And the way they did it, the way they cracked this nut, is almost as fascinating as the problem itself.
It's true.
So get ready, math fans, because we're about to jump headfirst into this world of graph theory, polynomials, and some seriously ingenious proof techniques.
Yeah, we're going deep.
So maybe we should start with a little refresher on what the conjecture actually is.
Okay, so at its core, the tree packing conjecture deals with trees, which are connected graphs with no cycles, and it also deals with complete graphs, written as Kn, where every single pair of vertices has an edge connecting them directly. The conjecture says that if you have a sequence of trees, T1, T2, and so on, up to Tn, where each tree, let's say Ti, has I vertices, you should be able to fit all of these trees into a complete graph, Knn, without any of the edges overlapping.
So it's like we've got this set of trees that keep getting bigger, and we're trying to fit them all neatly into this complete graph. And of course, we can't let any of the branches, the edges, touch.
Precisely. And while it might seem like you could always do this, especially since Kn is super connected, Actually proving it with hardcore math is where things get really interesting and tricky.
And that's where this new breakthrough comes in, right?
Yes.
This team of mathematicians, they didn't just prove the conjecture, they found a really elegant way to do it. They did this whole thing where they turned trees into functions, and then they used this thing called a polynomial certificate.
The polynomial certificate. It's brilliant. Think of it this way. They took a problem that was all about visuals, about graphs, and translated it into the language of algebra. It's a whole new way of looking at this problem that had everyone stumped for so long.
That's cool. So let's break down this polynomial certificate thing. It sounds kind of scary, but I have a feeling you can make it make sense.
I'll give it a shot. Okay, so they built this special polynomial. It's written as PEG, with a little g at the bottom, and then XY. The G stands for a sequence of what we call augmented functional trees. Basically, imagine a tree where you've picked a root and then make sure there's only one path from each vertex back to that root. That's your augmented functional tree. Now, this polynomial is set up in a really clever way. If you plug in values for the variables, x and y, and you can find even one combination where the entire polynomial doesn't become zero, then boom, the tree packing conjecture is true for that sequence of trees.
So it's like this polynomial is a truth teller for the conjecture.
In a way, yes.
If PG of xy isn't always zero, then the conjecture holds up. But how do you even go about proving that a polynomial, especially one that's based on all these tree structures, isn't always zero? I mean, that sounds crazy hard.
That is a fantastic question. Proving directly that a polynomial isn't always zero is, yeah, it's a beast of a problem. So they got smart and decided to look at it from a different angle. They used what we called modular arithmetic.
Modular arithmetic, huh? Isn't that like the math of clocks and remainders? Like, what does that have to do with these polynomial equations?
You're exactly right. It's all about those remainders. Instead of trying to wrestle with the entire polynomial PG of xy all at once, they looked at what was left over after dividing it by a specific set of other polynomials. These are written as, well, it's a bit complicated to say, but imagine a bunch of xkvn terms where kv are part of zn times zn.
Interesting. So it's like they're looking at the leftovers, the shadows of the original polynomial after it's been divided up. But how does that help them figure out if the original one is ever zero or not?
That, my friend, is the beauty of modular arithmetic. They were able to show that if the remainder you get after dividing PG of xy by these specific polynomials isn't zero, then the original polynomial itself can't be zero all the time either. It's like a magic trick, but with math.
Okay, I'm starting to see how clever this all is. But even with this new way of looking at it, actually calculating those leftovers, those remainders, and then proving they aren't zero, that's got to be some next level math, right?
Oh, absolutely. And that's where they pulled out another trick from their mathematical toolbox, Lagrange interpolation.
Oh, wow.
This technique let them rewrite PG of xy in a way that made those remainders much easier to work with. Imagine taking this big, complicated polynomial and finding a way to break it down to see its hidden structure. That's what they did.
So Lagrange interpolation is like the way they reorganized the problem to make those remainders make more sense.
Yeah, exactly.
But they still had to prove those remainders weren't zero.
Yeah, that's right, they did. And that's where the real genius of this whole proof comes in. They came up with this incredibly clever technique, and they call it the composition lemma.
The composition lemma. It sounds important. So what's the idea behind it?
Okay, imagine trying to prove something is true for like a gazillion different things, an infinite number.
Yeah, good luck with that.
Right. Like trying to do that directly would be a nightmare.
Yeah.
That's where the composition lemma swoops in to save the day. It basically says, hey, let's break this monster problem down into bite-sized pieces that we can actually handle.
So instead of looking at that whole polynomial PG of xy, for every possible sequence of trees all at once, they found a way to analyze it in smaller chunks.
You got it. And they start with the simplest tree you can think of. A star.
A star. Like a Christmas star. What does that even mean in, like, tree language?
Good question. In graph theory, a star tree is one where all the vertices are directly connected to the root. Picture it like a hub with spokes radiating outwards.
Okay, I'm picturing it.
And you know what's great about star trees? They're super easy to pack into a complete graph. Each vertex just needs one connection to the root, so you can fit a ton of them in KNN without any edges bumping into each other.
Right. Kind of like if you're trying to fit a bunch of straight lines into a box, you can fit way more if they're all pointing in different directions than if they're all clumped together.
Perfect analogy. And because packing star trees is so straightforward, proving that our tree packing polynomial, that PG of y isn't always 0 for a sequence of star trees, that becomes a much easier problem to tackle. It's like laying the first brick in a wall. You need a solid base to build on.
So they've shown that the polynomial works, or at least it's not always 0 when you're dealing with a bunch of these star trees.
Exactly.
But how do they go from these simple little stars to all those crazy complex trees the conjecture's actually talking about? That seems like a huge leap.
And that, my friend, is where the composition lemma really shines. They figured out a way to take your original sequence of trees, the G0, Gn, all the way to Gn-1, and they transform it into a new sequence made up entirely of star trees.
Wait a minute. So they're like changing the trees, messing with their whole structure, but somehow they're keeping that special property of the polynomial not being 0. That sounds like mathematical sorcery.
It kind of does, doesn't it? Okay, let me try to make it a little less mysterious. Remember those edge label polynomials we talked about earlier, the EIU and EJV? Each one of those is like a little code that tells you how two vertices in a tree are connected.
Yeah, and each one is like a little equation, right? Like yxi gi of u times yxiu or something like that.
You got it. Now here's the kicker. The researchers realized that by combining these edge label polynomials in a specific way, they could essentially rewire the connections inside the trees. They could take those complex trees and step by step morph them into those simple star shapes.
Okay, I get the picture. But how does this rewiring help prove the polynomial stays non-zero throughout this whole process?
That's the heart of their argument. Every time they make one of these strategic changes, every time they rewire the tree structure, they show that the new polynomial is still connected to the original one. They're basically proving that if the original polynomial wasn't 0, this new transformed one can't be 0 either. It's like a chain of logic where each link is unbreakable.
So they're like leading this polynomial, this truth teller, through a maze, carefully making sure it doesn't disappear on them.
Exactly. And finally, after a bunch of these carefully planned moves, they end up with a sequence of just those easy-to-work-with star trees. And remember, we already know the tree-packing polynomial isn't always 0 when you're dealing with star trees.
It's like they worked backwards, starting from a place where they knew the answer, and then retracing their steps to prove it's true for the more complicated cases, too.
Precisely. And by doing that, they've effectively proven the tree-packing conjecture for any sequence of trees you can throw at it.
Wow. It's incredible how they took this problem that had everyone stumped for like 50 years and cracked it wide open using this super elegant mix of graph theory, polynomial wizardry, and this ingenious composition lemma thing. But before we get totally lost in all the math, I think it's important to remember this is about more than just, theoretical equations.
Right.
This breakthrough could have huge implications for, like, the real world.
Absolutely. The applications of this proof are vast, and frankly, they're incredibly exciting. But I think we should dive into those fascinating possibilities in our final act.
Okay, so we've gone really deep into this whole tree packing conjecture thing, looked at the proof, and all the clever tricks they used to solve it. But something tells me there's more to this story. You mentioned something about far-reaching implications.
Oh, there definitely is. See, the tree packing conjecture might seem like it's stuck in this theoretical world of graphs and math, but its impact reaches way beyond that. We're talking real-world applications here.
Okay, now you've got me hooked. What kind of applications are we talking about?
Well, let's start with a field that's getting more complex every day: network optimization.
Right, networks. The backbone of, well, pretty much everything these days, from the internet to transportation to how we connect with each other. So how does this tree packing conjecture fit into all of that?
Think about it. In any network, you've got these points, these nodes that could be anything: devices, locations, even people. And these nodes are connected by edges, which are like the paths that let things flow between them.
Okay, I'm with you. So the nodes are like the vertices in our graphs, and the edges are those crucial connections that allow for communication or whatever it is that needs to flow through the network.
Exactly. Now, let's say you're trying to design a super efficient communication network. You want to use the fewest resources possible, the least amount of wire, so to speak, but still make sure the data gets where it needs to go quickly and reliably. This is where understanding the tree packing conjecture can be incredibly valuable.
I see what you're saying. It's like finding the most efficient way to pack all those lines of communication, those trees of information, into the network without causing any bottlenecks or overlaps.
That's the idea. By understanding how to optimally pack the flow of information within the constraints of the network, we can potentially create communication systems that are more robust, adaptable, and cost-effective.
So what you're saying is this seemingly abstract mathematical problem about trees and graphs could actually lead to real-world improvements in how we design and optimize the networks that power our lives.
Yeah.
That's pretty cool, but are there other areas where this breakthrough could have an impact?
Oh, absolutely. Let's move over to the world of computer science for a second and talk about data structures.
Data structures, right. The way we organize and store all that digital information that makes our computers work. Things like databases and algorithms, right?
Exactly. And guess what plays a huge role in a lot of data structures? You got it, trees. Trees offer a really elegant and efficient way to structure information for easy storage and retrieval.
Okay, I can see that. Think about something like a file system on a computer, right? You have the main folder, the root, and then branches leading to subfolders, and so on. It's like a tree.
Precisely. Now imagine dealing with massive amounts of data. I mean, truly enormous data sets. We need smart ways to store all that information so we can access it and use it effectively. And that's where understanding the tree packing conjecture, even if you're not a mathematician, could lead to breakthroughs in data management.
So by understanding the limits of how we can pack these tree-like structures of information, we can potentially design more efficient databases, faster search algorithms, maybe even new ways of compressing data for storage and transmission. It's like finding the perfect way to organize a giant library so that any piece of information can be found quickly and easily.
That's a fantastic way to put it. And as we move further into this age of big data, where the amount of information we're dealing with just keeps growing, these kinds of insights become even more critical.
This is all so fascinating. It's amazing to me how this one mathematical problem, something that might seem purely theoretical, has the potential to impact so many different aspects of our technological world.
It really is, and I think it highlights something really important about mathematics in general. It has this incredible power to uncover hidden connections and provide a framework for understanding the fundamental structures of our universe. The proof of the tree packing conjecture is a perfect example of how even the most abstract mathematical thinking can lead to tangible, real-world discoveries.
It's been an incredible journey exploring this with you today. A huge thanks to our expert speaker for guiding us through the intricacies of the tree packing conjecture and its surprising implications. And to all our listeners out there, remember that the pursuit of knowledge is a journey without end. And sometimes it's those unexpected detours, those journeys into the abstract, that lead to the most profound discoveries. All right, everyone, ready to dive in? We've got a good one today, finally cracked after almost 50 years, the tree packing conjecture.
Yeah, a real head scratcher for a long time.
And the really cool part is how this solution came about. It's not just number crunching, it's really elegant, bringing together graph theory and polynomial algebra in a really cool way.
Shows how interconnected math can be, right? I mean,
Yeah.
the tree packing conjecture, it's almost obvious when you see it visually.
Right, you just look at it and you're like, yeah, this tree should fit in the graph.
But actually proving it, whole other story. And that's what made this such a challenge for so long.
So let's back up for a second. For those who haven't been doodling graphs over their morning coffee, what exactly are we talking about with this whole tree packing idea?
Sure. So we start with a complete graph. We call it KNM, n vertices, every vertex connected to every other vertex.
Maxed out on connections, basically.
Exactly. Now, we're talking about packing trees into this graph, but not just any trees. We've got a specific set of n trees, starting with one that's just a single vertex, then one with two vertices, and so on, all the way up to a tree with n vertices.
So one vertex, two vertices, three vertices, all the way up to n.
Yep, and the tree packing conjecture basically says you should always be able to fit this whole set of trees into your GAN, no overlapping edges or anything.
Like a perfect jigsaw puzzle.
Yeah, but proving that you can always do that no matter how complicated your trees get, that's where mathematicians were stuck for so long.
Because it just seems so, I don't know, visually straightforward.
Right, and that's part of what makes this new proof so interesting. Instead of trying to force it with geometry or combinatorics, they found this really elegant approach using functions.
Functions, huh? Like fx and all that. Not the first thing that comes to mind with trees and graphs.
Yeah, it's a really clever shift in perspective. Basically, instead of picturing these trees with branches and nodes, they thought about them as functions that describe how the vertices are connected.
So each tree gets its own little function.
Exactly. And using this functional representation, they were able to bring in the big guns of polynomial algebra, which gives you all sorts of powerful tools for analyzing these kinds of relationships.
I'm starting to see where this is going, turning a tree problem into a polynomial problem.
And at the heart of it all is this really cool thing called the Tree Packing Polynomial Certificate. Sounds fancy, right?
It definitely piques the curiosity. Polynomial certificate.
Yeah.
What is it? Some kind of mathematical seal of approval for our tree arrangements.
In a way, yeah. It's essentially a function that encodes all the information about our trees and the complete graph all bundled up into a single polynomial.
So it's like this polynomial holds the blueprint for our entire tree packing situation.
Exactly, and here's the really ingenious part. The way they constructed this polynomial, it acts as a kind of truth tester. If the polynomial, after you simplify it as much as possible, still have any variables in it, then, guaranteed, your trees can be packed into the complete graph without any overlaps.
Wait, so just by looking at the structure of this polynomial, we can tell whether our trees will fit together nicely.
That's the beauty of it. If it's what we call non-zero, meaning it doesn't just collapse down to a number, then we're good to go. The trees can be packed.
That's some elegant math right there, no two ways about it. But how do we even build this magical polynomial in the first place?
It's a bit involved, but the basic idea is that you represent each tree as a function, we'll call them GK, where k goes from 1 to n for our in trees. And then we combine these functions in a specific way, using variables x for the vertex labels and another variable y that helps us manipulate things. That gives us our tree packing polynomial certificate, PGXY.
I have a feeling that Kaya's variable is doing some heavy lifting behind the scenes.
It definitely plays a crucial role, but before we get lost in the nitty-gritty of how to actually build the polynomial, let's talk about how it's used in the proof, because that's where the composition lemma comes in.
Yes, the composition lemma. You mentioned it earlier. It's like the engine driving this whole proof, right?
It's spot on.
Yeah.
Remember how we're representing our trees as functions? The composition lemma gives us a set of rules, or moves we can make, to change these functions in specific ways without breaking the rules of the tree packing conjecture.
So we can rearrange our function trees, but only in very specific, allowed ways.
Exactly. And these allowed moves let us, step by step, transform our starting set of trees into a configuration that we already know can be packed into KM, a set of star-shaped trees.
So we're strategically morphing our trees into something simpler, something we already have an answer for.
Precisely. And through this whole process, our tree packing polynomial certificate, it's like our guide and our safety net all rolled into one. Every time we make one of these allowed transformations from the composition lemma, we check our polynomial and make sure it's still non-zero. If it is, we're good to keep going.
So it's like the polynomial is making sure we don't accidentally make any illegal moves as we rearrange things.
Exactly. And the really cool part is that by making a series of these allowed moves, we can transform any set of n trees that fits our criteria into those nice, simple, star-shaped trees. And since we already know that star-shaped trees can always be packed,
we've proven that the original trees must be packable too. It's like this chain of logic, each link held together by the non-zero-ness of our trusty polynomial.
A beautiful way to think about it. And that, in essence, is how they finally cracked the tree packing conjecture after all these years. All right, so let's dig into this tree packing polynomial certificate. Remember, it's written as PGXY. X handles all our vertex labels, and Y, well, that one's our helper, our auxiliary indeterminate.
All right, so each tree gets its own function, and they all come together in this polynomial. But we're working with vertices and edges. How does the polynomial actually capture those relationships?
That's where the structure of PGXY comes in. It's basically the product of two main parts. We have VX, and we've got GXY.
VX and EXY. Let me guess, something to do with vertices and edges.
You got it. VX takes care of the vertices, and EXY handles the edges. Let's start with VX.
Vertex time it is.
So VX is designed to make sure that no two vertices in the same tree end up with the same label.
Makes sense. Each vertex needs its own unique ID in the graph, right?
Absolutely. And VX pulls this off using a product. That's what that symbol means. The actual formula is VX, ZX, ZXC, XK.
Let's take breaking it down.
Basically, XT V represents the label we give to vertex V in tree K. This double product, it's just a clever way to go through every single pair of vertices within each tree and make sure their labels are different. If we ever ended up with two vertices in the same tree having the same label, this whole VX thing would just collapse to zero.
So VX, it's like the bouncer at the vertex club, making sure no two vertices show up with the same outfit.
Love that analogy. Now, over to EXY, which, as you probably guessed, is all about the edges. This part ensures that no two edges from different trees try to occupy the same spot in our complete graph.
So EXY, it's like air traffic control for our tree edges, preventing any midair collisions.
Exactly. And here's the formula for that. EHE-AKY, 7Y. Now, don't let this big, scary expression scare you off.
My brain's still trying to process all those symbols.
All we're doing here is comparing the edges of every pair of trees, I and J. We use the functions that define those trees, G and G, along with our trusty vertex labels, to see if any two edges are trying to connect the exact same two vertices. And you guessed it, if we detect an overlap, this whole e to y expression goes straight to 0.
So we've got VX keeping the vertex labels unique and AXY making sure no edges bump into each other. Both have to work perfectly for our tree packing polynomial certificate to give us the thumbs up.
You nailed it. And remember, we're not after some specific number here. When we say non-zero, we just mean the polynomial shouldn't simplify down to a single number. It should still have some variables hanging around in its final form.
Right. It's the polynomial structure, its DNA, that matters, not a specific calculation.
Exactly. That non-zero-ness, that's our guarantee that we can pack our trees without any conflicts.
Okay, starting to see how powerful this polynomial is. But how does this connect back to the composition lemma? You mentioned it gives us rules to transform our trees. How does it actually play out?
That's where the real ingenuity comes in. With the composition lemma, we can change our tree functions in a way that reflects those allowed transformations, like attaching a branch to a different point on the tree. Each time we make a change, we check our polynomial, PG, If it stays non-zero, we're in the clear. Those modified trees can still be packed.
So we're tinkering, but the polynomial's always there, double-checking our work.
You got it. And the cool part is that through a bunch of these allowed moves, we can reshape any set of trees that fit our criteria into those star-shaped trees we talked about earlier.
In star-shaped trees, those we know we can always pack neatly into Can-An. It's like we're taking a really complex tree puzzle and step by step, turning it into a much easier puzzle, one we already know how to solve.
Exactly. And because our tree packing polynomial certificate, it stays non-zero throughout this entire process.
We know for sure that our original set of trees, those must have been packable too. It's a beautiful chain of logic, all thanks to the power of that non-zero polynomial.
A very elegant way to put it, and that, my friend, is the essence of how they finally cracked this 50-year-old math problem.
Okay, so we've got this proof, and it all hinges on transforming our original trees into those star-shaped configurations, all guided by our trusty tree packing polynomial certificate. But I'm still a little fuzzy on the specifics. Can we actually see the compositional lemma in action? Like, how do we use it to make these transformations?
Absolutely. Let's say we have a tree, we'll call it T, and it has 4 vertices labeled 1, 2, 3, and 4. Vertex 1 connects to vertex 2, and vertex 2 connects to both 3 and 4.
Okay, I'm picturing it kind of like a lopsided Y.
Perfect. So let's say we want to use the composition lemma to change this tree a little. We can take vertex 4 and graft it onto vertex 3 instead.
So instead of vertex 4 connecting directly to vertex 2, it would now be hanging off of vertex 3.
You got it. Essentially, we're just redefining the function that describes our tree. Originally, it might have been something like G1 equal 2, G2, G3, G3, G4, log 2, showing us the connections. But after using a composition lemma, our new function would be G1 marrow do G2 all 3, G3 all 2, and G4 it is 3. See how we've just moved the attachment point of vertex 4?
Yep, it's like we've done a little tree surgery, reattached that branch, and at this point, we'd take our new function, G, plug it back into our tree packing polynomial certificate, make sure we're still following the rules.
Right, exactly. We want to make sure that non-zero-ness still holds true. And if it does, we're good to go. Our modified tree, grafted branch and all, still fits within the tree packing conjecture. And we can keep doing this step by step using the composition lemma to reshape our trees until we end up with those nice star-shaped trees that we know are always packable.
Really elegant solution. Gotta hand it to those mathematicians. They took this problem that seems so visual, all about fitting shapes together, and they tackled it with these powerful abstract tools like functions and polynomials.
It really shows how interconnected math is. You've got graph theory, algebra, even a bit of topology when you think about those connections, all coming together in this really beautiful way.
It's a good reminder that sometimes the most elegant solution, it comes from finding the right language, the right perspective to view the problem. And in this case, that language was the language of functions and polynomials.
Couldn't have said it better myself. And this breakthrough, after 5 decades, it makes you wonder, What other seemingly impossible math problems are out there just waiting for the right approach?
Exciting to think about, isn't it? Somewhere out there are these elegant solutions hidden in the world of math, just waiting to be discovered. And hey, maybe one of our listeners will be the one to find them.
Wouldn't that be something?
It sure would. Well, that wraps up our deep dive into the tree packing conjecture. We've traveled through decades of mathematical thought, seen the power of functions and polynomials, and we've witnessed the satisfying aha moment of a problem finally being solved.
And who knows what other mathematical mysteries await.
Exactly. Yeah. So until next time, stay curious, keep those minds sharp. You never know what breakthroughs you might find. All right, ready for a deep dive into some graph theory?
Always.
We're tackling the tree packing conjecture, a real head-scratcher since, well, 76.
Big year.
Huge. We've got this fresh-off-the-press research paper dated October 18th, 2024, claiming they finally cracked it.
And you know, what's really interesting about this one, this proof, it's how they bring in these really elegant concepts, but from all over mathematics. It's not just, graph theory.
Right.
It's like combinatorics, a little bit of abstract algebra sprinkled in there, the polynomial method. Gotta love it.
Oh, you had me at polynomial method. But for our listener, who maybe this is like their first foray into this kind of math, what are we even talking about here? What is this conjecture?
Okay, so picture this. You've got a complete graph. That's where every 2 points, every 2 vertices have a direct line, an edge between them.
Okay.
The conjecture says no matter how many points you've got in this graph, you can always sit in the same number of trees, but each tree has a specific number of branches.
Wait, hold on. Trees, like branches and leaves trees, in my graphs.
Yeah, it sounds a little wild. But in graph theory, a tree is just this branching structure, like one edge, then 2 branching off, then maybe more from those.
Okay, so we're fitting these branching things into the graph, but they got to fit perfectly.
Exactly. Each edge of the tree got to line up with one of the edges in the complete graph. No overlaps, no leftovers. Think like a super precise jigsaw puzzle, but with, branching structures.
Oh, okay, yeah, I see where this gets tricky. Especially as the graph gets bigger, more points, more trees to cram in there.
And that's what makes this such a bear. Sure, it feels like you should be able to, right? But proving it works for any complete graph. Mathematicians have been trying that for decades. We had proofs for certain cases, but this general one, that was the holy grail.
So this paper, this is them saying we found the grail.
They say so. And their approach, it's pretty clever. They stopped thinking about trees as like these drawn out things and started thinking functions.
Hold up, functions. Like fx from high school algebra.
Yep. It's a total mind shift. See, a tree's about relationships, right? One point connected to others. Well, a function's the same. Input, output, all linked up.
So instead of drawing it, they made it like a math equation.
Basically, each point in the tree becomes a function. It's like instead of speaking English about trees, they switched to, like, I don't know, Mandarin. Same idea, whole new toolkit.
And that helps. How?
Because now they can use all these powerful tools from other parts of math, specifically the polynomial method.
Ooh, okay. I feel like we need to hold on a sec for our listener to catch up. So we're trying to prove you can always pack these trees into a graph no matter how big. And now these mathematicians, they're using functions instead of drawings.
Exactly. Pretty neat, right?
But how does that even connect to, the actual problem?
Because that is what lets us use something called the polynomial method. But we can talk about that more after a quick break.
Sounds like a plan. All right, so polynomial method, lay it on me. We've got the trees speaking function. What's next?
Okay, so the polynomial method, it's like this. You take a problem about shapes and arrangements, like our tree packing puzzle, and you turn it into a problem about equations.
Okay.
So these researchers, they built this special polynomial, it's like a fingerprint, but for the tree packing problem, they call it the tree packing polynomial certificate. Catchy, right?
Polynomial certificate. I mean, I get the polynomial part from, back in the day, but what's so special about them in this case?
Think of a polynomial like a little machine.
Okay.
You put in information, that's your variables, and it spits out a result. And the way that machine is built, its structure, it tells you something about the info you put in. So for this tree packing polynomial certificate, they designed it so it only works out if you can actually pack the trees correctly.
So the polynomial knows if we've messed up the packing.
Exactly. If we try to put 2 tree branches on the same edge in the graph, boom, the polynomial goes to 0.
It's like a mathematical alarm bell.
Right. So to use this thing, you plug in values for the variables, Those represent how we're trying to arrange the trees on the graph. If there's any conflict, polynomial screams 0, means nope, can't pack them that way.
And if the polynomial doesn't go to 0, we're good.
Potentially, but to be absolutely sure, the polynomial can't be 0 for any possible arrangement of the trees on the graph. If that checks out, then we know for sure a valid tree packing exists no matter what.
So we turn this visual puzzle into this equation, and if the equation works, the puzzle's solved.
That's the beauty of math. You can connect these totally different ideas and boom, you've got a new way to attack a problem.
Okay, so how'd they even come up with this tree packing polynomial? What's the recipe?
It's a bit much to, spell out here, but the gist is each tree gets its own little piece of the polynomial. It's a factor, and they're all multiplied together. And those factors, they use variables that represent the edges of our complete graph. And the whole thing is set up so that if there's a conflict, like two tree edges trying to be on the same graph edge, bam, the whole thing goes to 0.
Okay, so this polynomial's got all these potential clashes built in, but how do you analyze something like that? Especially if the graph is huge, that polynomial could be a monster.
Well, that's where you bring in the big guns, mathematically speaking. Things like the multivariate quotient remainder theorem. Sounds intimidating, but it's a lifesaver here.
I'm trusting you on this one.
Basically, these tools let you figure out what a polynomial does without having to check every single combination of variables. It'd be like trying to find if a number is prime by dividing by every number less than it possible, but who's got the time right?
Right.
These theorems, they're like shortcuts.
Okay, so we've got our polynomial, we've got our fancy math shortcuts, but the tree packing conjecture, it's about any complete graph, right? We've just got this one polynomial. How does that prove it for, like, infinity graphs?
That is where things get really, really clever. They use something called the composition lemma. It's like a strategy to break the problem down.
Okay, I like where this is going. A lemma, it's like mathematician speak for a secret weapon, right?
Pretty much. So instead of doing the whole shebang at once, they're like, what if we just make the graph one vertex bigger at a time?
Oh.
And the composition lemma, it's this set of rules that says if you can pack the trees in the smaller graph and you add one more vertex in its tree this way, you're guaranteed to still be able to pack them.
So each time you add a bit, this lemma makes sure you're not breaking the packing.
You got it. Like building a tower, but each layer you add, you've got this guarantee it won't fall over. And since you can keep adding layers forever, boom, you've proven it works for infinitely many cases.
That's so cool. But I feel like we should pause, make sure our listener is following all these twists and turns. What do you say?
Absolutely.
Okay, so last we left off, we had this composition lemma, our blueprint for packing trees one step at a time. But how do we know this blueprint won't, like, lead us astray? How's the guaranteeing we're always building a valid tree packing?
Right. So remember how we built that tree packing polynomial? How it was designed to, like, sound the alarm if things went wrong?
Yeah, the 0 alarm, right? The two tree branches ended up on the same edge.
Exactly. So this composition lemma, it's not just telling us how to add a new vertex in its tree to our graph, it's also telling us how to change the polynomial to match.
So we're, like, updating our blueprint as we build, making sure it still works with the new stuff.
Exactly. And get this, the lemma doesn't just say, oh yeah, you can make a new polynomial. It says, if your old polynomial worked, meaning no zeros, no clashes, then this new one will work too.
So it's like each step, it's guaranteeing the next step is going to be all right.
Think of it like a chain. Each link is strong because the one before it was. We start with a small graph. We know the packing works there, so the polynomial works. Then each time we use the lemma to make it one vertex bigger, that new polynomial is also guaranteed to work, meaning that bigger graph can be packed too.
And because we can, in theory, keep doing that forever.
We've proven the tree packing conjecture for all complete graphs. We don't have to check every single size because the lemma gives us this chain reaction of proof.
That's amazing. You start with, like, this specific polynomial, and then by using this lemma, you've basically proven something about an infinite number of graphs.
Welcome to the power of mathematical induction. You show a starting point is true, and then you show that if it's true for some case, it's got to be true for the next one too, and boom, you've covered all your bases.
That's incredibly elegant, though I imagine actually working through the details of this proof, it's got to be pretty intense, right?
Yeah. Oh, absolutely. This is not back-of-the-napkin math here. But even for those of us who don't spend our days wrangling polynomials, you got to appreciate the beauty of this approach. It's not brute force. It's about finding the right perspective, the right tools, these elegant arguments to crack a problem that's been bugging mathematicians for almost 50 years.
It really shows you how powerful abstract thinking can be, right?
Yeah.
I mean, we started with trees and graphs, ended up with functions and polynomials and lemmas.
And along the way, we've uncovered something fundamental about how these structures work, how they fit together. This wasn't just about solving one problem, it was about gaining a deeper understanding of graph theory itself.
And who knows what other insights we might find building off of this, right? It's like opening a door to a whole new area of mathematics to explore.
Precisely. And that's what makes this field so exciting. Who knows what other seemingly impossible conjectures are out there, just waiting for the right mathematician with the right set of tools, the right lemma, to come along and crack them wide open.
Well, on that note, to our listeners, if this deep dive has sparked your own curiosity, we encourage you to dive into the world of graph theory. You might be surprised at what wonders you uncover.